Now, synaptics. Okay. Hello, hello. All right. There we go. Okay. Now, all right, I'm shocked that this may actually work, but we'll hope for the best. Now, COVID rules. Okay. Until this wave passes, we're going to try to be very careful. And especially, I don't want you infecting me. So, we'll do what we can to keep everybody safe. And I did forget my laser pointer today, so I'll just be pointing at things with my pen probably. But first order of business is to figure out who's sitting where. So I got Dwayne because he asked first. So what I'm going to do is record your seat on this seating chart. This is where I want you to sit for the rest of the semester until we hear that we don't have to worry about this anymore. And that's probably not going to be this fall. All right? Now.
Wait, I'm sorry, I didn't hear what you're saying.
Hello?
Yeah, I caught the end of what you were saying.
Oh. Are you not hearing this microphone? Christian is, okay.
I hear you loud and clear.
Well, if you're not here, if you're zooming in, then all we're doing right now is just figuring out who's sitting where. So nothing's happening yet. Everybody got that?
Hi, I have just one question. I'm so sorry.
Yeah.
I went to room 1053, and there's a different class in there. What classroom are we in?
We are in Millenberg Hall 165.
165. Thank you very much.
Right. The biggest hall on campus. Okay. So Cassidy Ankar. Well, that's a great start. Mariana Bardalis. Wow. Haley Bolio. Okay, let's see, 1, 2. And Spencer Beck. Okay, what row are you in? Is that like 7? Okay. 7, and you are over there. And Jessica Billiot. Okay, and that's what, 5? And Kelsey Boudreau. 1, 2, 3. 2, 3. Yeah. What a pain. Crystal Brown. Ivy Bui. Okay, you are in 6, or no, you're in 4. Right. Let's see, Christopher Bui. Okay, and that is 1, 2, 3, 4, 1, 2, 3. Okay. Four. Rolando Castro. Okay, you might want to come down further because if you're back behind row 12 or so, you're going to miss some of the text on the slides. We did have a look at it. So what row are you in? 9? Kurutal Chima, okay? And Melina Chester. Okay. And Jason Cook. Okay, and row 8. Okay, and let's see. Zana Cordes. Nope. Okay, and you're in 7. Okay. Sorry? It's 6. Okay, yeah. Dwayne, we got you. Kaylee Cross. And what row? 6. And all right, 6. Lindsay Dang. 6, and let's see. Jamark DeSala. Danny Din. Okay, you're on 1, 2, 3. Okay. Hien Do. Okay. 4. Okay. Trent Dumpster. Trent. Jose Figueroa. Okay, 8. Okay, 8. And Clark Fetchinger. Or did I? No, Fletchinger. Okay. Alyssa Florent. Ten. Okay, and Anthony Forrest. Alana Frick. Jasmine Garcia. I see it, yeah. Rami Hassan. And okay, all right, I see you. Michael Ho? Laura Hollenbeck is on the screen. Okay. Shania Hollins? Abrar Ismail? No. Joseph Trishunda? Or Trishunda Joseph, sorry. And you're in 1, 2, 3, and 1, 2, 3. Akib Kamaruddin? Akib? Caden Connect? Christian Louvier?
Here on Zoom.
Okay, thank you. Michelle Liu? And Megan Mai? Mike McCombs? Ana Sofia Molina? You're in 4. Let's see. Madison Malaire? Gotcha. Casper Morvant? Sylvia Mullen? On the screen?
On Zoom.
Yep, gotcha. Okay. Luai Nasser? Amy Wynn? Diana Wynn? Okay, 6. Justin Wynn? Oops, wrong. There you go. Okay. Kayla Wynn? Madison O'Malley? Alexander Pearson? Ashley Prospery? What's that? Yeah. Right. Exactly. Alexis Revere? Okay. Kristen Ricard? You may want to move up a little bit when you see the text on some of the slides. It's going to be a little bit small for someone that far back, but you can be there for now. But you gotta tell me if you move. Okay, where are we here? Michael Sultana. Abdullah Syed. Okay, you're 11. Okay. Christopher Tejada. Okay. Kimuyen Tran. Matthew Tran. Okay. Haley Traherne. Okay. Almost done. Alexis Trosclair. Richard Trong. Katerina Trushina. Did I see you on the screen, Kater? Up. Okay. All right. Hannah Volpe. Sabrina Wadwa. Jade Willaz. Alam Yaya. Oops. Tasha Youngblood. Oops. Joshua Zickler. Sarah Zimmer. Okay, who have I missed? Because I saw people filtering in. Ah, okay. And what row are you in? Got it. Ah, 11. Okay, yeah, I was going to say, it didn't look like you were next to that person. Anybody else? Bardalas. I'll get Bardalas first, and you're in 9. And go ahead. Oh, Akib. Okay. What last name though? I've got it by last name. Okay. 30. And you're in row 6? 7. Okay. Anybody else? All right. So you saw me set up Zoom. We have to have this in case the university says we have to go remote. This is not something that I want. The class last fall had a terrible time. And I honestly don't think they learned very much. It was just too hard. relying on recorded presentations is just not the best thing for this class. You really sort of need to interact and to be able to ask questions, because this is sophisticated stuff. It will be difficult for you to learn some of these topics on your own. And for that reason, I wanted us to be face-to-face again this fall, as much as possible. So we're going to do our best. We will have Zoom recordings of every lecture, but as I indicated in my email to you, which I hope you all saw, all of the ways that we have to record these things require an internet connection. So if the internet is down, we have the ability to do the on-campus lecture, but maybe not record what we're talking about. So just be aware that your best defense against an unexpected exam question is to actually be here. And oh yeah, to do this frequently. Raise your hand and ask a question, because I guarantee if you have a question about something in this class, we have 69 enrolled, 65 others will have the same question probably. So just let's try to be as normal as possible, and let's learn some ecology. So what I want to do first is sort of give you a general introduction to the idea of ecology, and then I'm going to make the case for why ecology is important for us. Let me see a show of hands here. Who here is aspiring to a career in healthcare? Yes, that's pretty average for a biology class like this. Okay, so I will try to put that in context of why you need an ecology course. You must understand ecology to be an effective healthcare worker. Whether you're a physician, a nurse, another position, you must have some understanding of ecology. So let me start. Let me start by seeing if I can get this thing to advance. And it's not advancing. Why aren't you advancing? Gonna make me do it here? What? Gonna make me do that? Okay. So, yes.
This PowerPoint is still not posted on Google. You know what it was posted on Google?
I'm gonna post it right after lecture. Yeah.
Take notes on them.
Ah, yeah, you're right. Well, I made a few changes to this, and I just didn't get it done before class. So, because I'm helping 2 doctoral students try to defend their dissertations, and time is a little crunched at the moment. But ecology is the study of the relationships between organisms in their environment, and loosely speaking, it's the abundance and distribution of organisms in relation to the abiotic environment, that is the physical conditions, and the biotic environment, which is the other organisms they're interacting with. So we have a lot of interactions between species, and that very much resembles the way that humans interact in society. So it's no mistake that economics and ecology share a lot of theory. And Darwin referred to ecology as the economy of nature, which is where your text takes its title. So of all the sciences that you will be exposed to here at UNO, ecology is by far the youngest in terms of its knowledge base. Even genetics, where we've made enormous strides in the last 15 or 20 years, has an intellectual basis that goes back some hundreds of years. That's not true of ecology in the way that we think of it today. Ecology is very new. Some of the branches of ecology were invented as recently as 1980. And we'll talk about all of them in this course. Now, will you let me? Oh yeah, there you go. Okay, so the main thing I want to communicate today about the way we are going to approach this course is that ecology has a hierarchical organization. And it's not even one science. It's 4 different sciences. And each of them builds on a level of organization below it, but has unique questions, unique properties, and unique analytical approaches. So basically, when you sit in this room, you are taking physics, chemistry, biochem, and microbiology all in the same semester. That's what this is like. Now that raises an important point. Do you use the same methods to study for physics, chemistry, biochem, and physiology? No. But what usually goes in a course for an entire semester, at least is, a relatively consistent theme and way of approaching things, that's all out the window. We will shift from conceptual to mathematical to graphical to conceptual. You're going to have whiplash at some point, and I guarantee every one of you will struggle on at least one exam. That doesn't mean that people don't get A's in this course. So just try to keep it in perspective. The vast diversity of questions that we address in ecology is going to expose your weakness at some point. Just do your best and work hard. So let's look at this hierarchical organization. We work on individuals. We work on the adaptations of individuals to their environments. We try to understand what about the environment produces those adaptations. We also work on populations, which are collections of interbreeding individuals. We work on communities, which are associations of different species populations. We work on ecosystems, which is really sort of not about organisms at all. It's about matter and energy. And organisms are merely buckets in which we place matter and energy. And it doesn't really matter if it's humans or if it's blue whales or krill. It doesn't matter. Ecosystem ecology has a very different focus from the other 3 that we've talked about, which are very concerned with organisms. Finally, there's the biosphere, the totality of all Earth's systems as they interact with one another. And at this point, we are grading into what people consider other sciences: atmospheric science, geology, oceanography, the big systems, but they overlap. And these are ecological questions. So let's take them one at a time and explore them a little bit, and maybe you'll start to see why we use such different methods and why this class will give you fits at some point. So in studying individuals, we're looking at the most fundamental units in ecology. And, oh, by the way, it's the only unit in ecology that has an objective physical existence. Since this is not a philosophy class, we're not going to argue the point. But I can poke you and you are an individual. Everything else in ecology is defined by the experimenter. So we're interested in the processes by which individuals acquire energy and nutrients, what happens to the waste that they produce. The reason that we think of them as physical entities is because they are membrane bounded. They have a clear boundary that delineates them from their environment. Okay, a species then is a collection of these individuals that are capable of interbreeding. And even that is kind of defined by the scientist who's working on it. I'm not going to go into the different species definitions because that's more of a subject for an evolution course. But when we move to populations, suddenly we have a whole different set of questions. It's not just what do individuals do, it's how many individuals are doing it. What are the characteristics of those different individuals? A population has no objective existence. It is defined by the person who is asking the question of the population. So you comprise a population. You are the population of individuals in this classroom. But you also belong to a much larger population, which is the population of students trying to get through UNO in the middle of a pandemic, right? So we don't necessarily have clear boundaries between populations, and they are defined not objectively, but subjectively by whoever's working on them. They have characteristics that individuals don't have. They have a range that they can inhabit on the earth. They have an abundance. The abundance of individuals is one, but the abundance of a population can take many values. They have a density, also something that individuals don't have. Okay, and they can be composed of different types of individuals. Communities then are collections of these species populations living together in time and space. Sometimes we can define relatively clean boundaries between communities, but as you will see, most of the time we cannot. They are also defined by the people who work on them. Okay. We will cover many interactions between community members: predation, competition, mutualism. And we'll spend a lot of time on that in this course. Finally, ecosystems, which is where we will stop in this course, are focused on the movements and dynamics of energy and matter. So as I said, organisms are simply a convenient bucket in which to store energy and matter before it moves from one type of organism or one type of compartment to another. So you have carbon in you. You are a compartment in an ecosystem for carbon. Carbon also exists in carbonate rock. And as far as ecosystem ecology is concerned, you are completely uninteresting except for the carbon in you. And what's interesting in ecosystem ecology is the movement, the dynamics of the movement of carbon from people into carbonate rock, from carbonate rock into people. So the amount of carbon, the rate of movement of carbon, and the energy that is involved in moving things around. That's what ecosystem ecology is interested in. Now, the entire biosphere is on our minds quite a lot these days, and we will make allusions and do at least a little bit of reference to the biggest scale phenomena that tie everything together. But there's a limit to what we can cover in one semester. In many universities, this is a 2-semester course. You do individuals and populations in one semester, communities, ecosystems, and the biosphere in the second semester. We don't have that luxury at UNO, so we're going to do the best we can. Now, we've seen that there are different kinds of questions. And the reason that there are different questions is that each of these levels has emergent properties. Emergent properties cannot be predicted from an understanding of a lower level of organization. Okay, and the example that I'm using is knowing how individual organisms reproduce does not tell you whether a population is growing, stable, or declining. You can't predict that just from knowing something about individuals. You must know specific information about the population. That is an emergent property. You cannot predict the trajectory of population growth just by knowing that on average, human females are producing 2.08 offspring per female per lifetime in developed countries. You have no idea what that means for the population. Okay. As a result, we can't rely as much on reductionist thinking as a lot of other sciences do. We have to try to understand the way that parts interact much, much more in ecology. The other thing is, think about the scale that we're talking about. Sure, we're talking about individuals, right? But that's really different from having a test tube full of chemicals. You can make that test tube full of chemicals repeatedly over and over and over. Every individual has a set of unique properties that may affect the outcome of an experiment that you try to do with it. We do not have the same level of experimental control in ecology that we do in, say, physiology or biochem. For that reason, we don't have as many definitive answers. And for that reason, I don't care nearly as much if you can recall an equation on an exam as you know what to do with that equation, that you know what the result of a calculation might mean. So on exams that you'll have in this course, yes, you'll be expected to remember things. But then you'll get the dreaded question, why? Explain why. Arguing from evidence, synthesizing what you know, and constructing a rationale for your answer is at least as important as knowing the facts in this course. Let me see that show of hands again about wanting to be in healthcare. Okay, so let's just imagine for a second that you've achieved your goal. Let's say you've finished your classes, you're in clinical rotations now. You go into a patient's room with a supervisor. What does the supervisor ask you? Does the supervisor ask you what the ideal gas law is? No. The supervisor asks you, interview this patient. Explain what is going on with this patient from the evidence. Construct an argument from the evidence. That is what we do here. If you make it to medical school and you make the rounds on a ward, nobody cares whether you can recall a particular equation. What they care about is what you can do with it. That's what I care about. I care about what you know about interpreting things as at least as much as I care about you remembering things. This course, more than most others at this university, gives you some practice in doing what you're going to be asked to do in the real world with the information that you're gathering. This course is not simply about the information, it's about what you do with it. So let's look at some of these, let's summarize what we're going to do here. We're going to look at adaptations of organisms and how they reflect the ability of an organism to survive in an environment. We're going to compare them in many cases using fitness, that is reproduction, relative reproduction, as a currency. We will look at populations and we'll ask what's their density, what's their distribution. We'll look at communities and ask, how do species live together and which species cannot live together and why? And then we'll look at ecosystems and we'll try to understand a little bit about the movement of matter and energy through different compartments. Now, why is this more important than physiology? Why is this more important than chemistry? As a physician, you are powerless in many, many respects. You are simply trying to do damage control as a physician. In ecology, that tells you where the damage is coming from. It tells you how to avoid the damage. Ecology, not medicine, determines our health and longevity. Ecology determines the sustainability of society. It's not going to do you much good to be a physician when you have 1,100 people with heat stroke trying to get into your emergency room. That's ecology. That's not medicine. Our current predicament is a great example. It is an ecological problem. It's not a medical problem at all. We and the coronavirus are a simple predator-prey system, which we will discuss in this course. More properly, I will use the term exploiter and victim because predator and prey is like a lion and a zebra. And you'll see the difference between COVID and a lion later in the course. But working with COVID patients in the hospital is the least effective, most expensive, and least efficient way of dealing with COVID-19. COVID-19 is an ecological problem that we screwed up, and we are paying the price. COVID is simply a zoonosis. Here is the accumulation of zoonotic disease outbreaks since World War II worldwide. Notice that this has happened about every 18 months. So COVID is not unique. COVID is almost destined to happen. You'll remember a politician saying something about the origins of the SARS-CoV-2 virus in rather unflattering terms. I'll call your attention to the number of zoonotic infections that arise in different countries. And I will call your attention to that red country right up there. Where's the shithole? Okay, let's be real about this. This is a worldwide problem. Notice that one of the blue countries way up there at the top is actually Finland. Who thinks of Finland as a hotbed of zoonotic disease? Nobody, right? Okay, so here are the US emerging diseases. La Crosse encephalitis, so you want to avoid living in Wisconsin. Lyme disease, you want to avoid living in the Northeast, although it's kind of spreading all over the country. HIV, of course. Notice the next one is Bayou. Oh dear, what's that all about? It's about Homa. We had a zoonotic disease originate in Homa. Sin nombre sounds vaguely Spanish, and in fact, it is a southwestern variant of that disease. Hantavirus. Okay, Black Creek is also a hantavirus. And of course, West Nile was a recent addition to North American diseases. So let's have a little humility here. Let's admit that what we're looking at is not unique to one country or another. And let's admit that understanding the dynamics of diseases is a really important ecological issue. And it will save time, money, and the lives of healthcare workers if we understand this at an ecological level. Now, this is really important. This is the lag time between the detection, the identification of a zoonotic disease and an outbreak. Now notice that. Now we've got some bad players here. We've got HIV, and HIV emerged in the US in the 80s, but it was first detected long before that in blood samples taken from people who were infected much earlier. In fact, we can trace the genetic history of HIV in quite some detail now. So we know that the first HIV case that we can reliably identify where clinical illness occurred was in the 50s. And that's a retrospective diagnosis because we had blood samples from that person who died. However, we also have blood samples from much longer ago, and we know that the current modern HIV family first emerged in Cameroon about 1908. That's a great question. So I want you to save that question for the lecture on the SIV model and parasites and diseases. But yes, it does. Okay, so notice that you've got other diseases that have frightened us periodically. There's Zika. Okay, Zika was identified in like 1940. And we didn't have an outbreak till much later. Marburg, which is, of course, a filovirus, very similar to Ebola. There you go. It was identified in Germany, of all places, even though it is a bat disease that is native to Africa. It had infected a monkey. The monkey had been imported to Germany. One of the workers got infected. So this lag time can be really profound. And the reason why we need to understand the dynamics of these predator-prey systems, loosely speaking, is because we don't always detect them at the time of the outbreak. Sometimes they're lying around and they ambush us. So let me see, I don't want to go over here. So also, welcome to political science. There's a lot of people who are making a lot of money off the way things are right now. They do not give a shit whether you live or die. They want money. And basically what they are competing for is the ability to be the last to die. They don't care if you're the first to die. They simply want to be the last to die. If that sounds harsh, I'm retiring. I don't care. I have been doing this for 30 years. I taught your parents. They did nothing. I taught your grandparents in some cases. They did nothing. They let you get into this position because they did nothing. I was at the first Earth Day, somewhat longer ago than I want to admit. And to me, it was a calling. That's why I'm an ecologist. To your grandparents, it was a party. However much you love people, you have to recognize that where we are now did not have to happen. The conversations we are having now could have been had 40 years ago. We would not be in this situation. taking climate change as an example, we knew what carbon dioxide was all about. In what year? Anybody? 1856. The projection of global warming as a result of the production of carbon dioxide was first elaborated in 1901. Every president since Lyndon Johnson has been informed of this. People just don't do things until it's too late, almost. So don't let it be too late. Learn something this semester and put it to use. Act for your own survival. Okay, and I want to close with the words of Jerry Garcia, someone I actually knew in San Francisco in the 1960s. Somebody has to do something, and it's just incredibly pathetic that it has to be us. That sums up our situation today as well as anything I can possibly say to you. You must work for your own survival now. And the other words I'll leave you with are from that bad boy Keith Richards of the Rolling Stones, who you may actually know better from Pirates of the Caribbean. But Keith got into trouble more than once in life, and if you're going to kick authority in the teeth, you may as well use both feet. If you take anything away from this course, I hope it's not simply the factual basis. I hope it's a determination to live. Okay. I will see you Wednesday. We will start with Global Climate System on Wednesday. For those of you who are in the Wednesday lab and your names start with A through HA, come prepared for an outside lab on Wednesday. You'll be going to a wet and muddy place. So bring boots, be prepared for rain.